Okay, thank you. So today I'm going to talk about Reynolds stress fluctuation properties. Actually going to look at a couple of very simple properties. I'd like to acknowledge my co-authors, Spencer Zimmerman, Jimmy Phillip, Yoshinobu Yamamoto, and Yuki Tsuji. So today we're going to look at the self-similar structure of the mean momentum balance, and from that infer a couple of conjectures that look at whether the self-similar behaviors in the mean flow structure are reflected in the turbulent motions affecting momentum transport, namely the Reynolds stress fluctuation. So an outline, I first have to go over a little bit of background of the analytical developments that talk about the similarity structure of the mean momentum equation. And then I'm going to briefly pose a couple of conjectures that relate to the properties of the UV fluctuations. Then we'll use some DNS and physical experiment up to large Reynolds number to investigate the veracity of these conjectures. And at the end, we'll do a PDF analysis using a Graham-Charlier representation to look at non-Gaussian effects that might influence the results. But there's a lot of uncertainties yet in what I'm going to talk about today. So the first part is just to talk about the similarity solution construction, and I apologize for having to go through this quickly, although I think a number of you have seen elements of this. I just need to make a few kind of key points before I can talk about how this influences the Reynolds stress. So we're talking about turbulent channel flow. Previous speaker went over that, so it's the same configuration. Half channel height is delta. We'll be talking about the mean velocity U. Reynolds shear stress is UV bar or UV bracket. And then the mean momentum equation is shown down here in the corner, where we have the Reynolds stress gradient or turbulent inertia balanced by mean pressure gradient and mean viscous force, the last term there. So in the process of determining the similarity solution, there's sort of three key things that happen. The first one is you have to determine the leading balance progression, and that's an empirical step, actually. But it's well established now, and the thing is you don't have to empirically determine the scalings of this progression. You just have to determine that there is a region near the surface, layer 2 we call it, where the viscous force and turbulent inertia are effectively in balance and much larger than the pressure gradient. There's a region where all three terms, layer 3, where all are of leading order, and then there's layer 4, where there's an inertial layer where the dominant balance is between the Reynolds stress gradient and the pressure gradient. So down here we have the, in the lower left-hand corner, we have the inner normalized version of this, and epsilon is 1 over, or epsilon squared is 1 over the Reynolds number when you normalize by inner variables. Okay, so that's sort of the first step. And then using that and a bunch of other stuff that I'm having to skip, and so I just want to get to the gist of this. What I want to talk about is there's an internal hierarchy of scaling layers, and this is constructed effectively by using a surrogate coordinate, which has to do with the decay rate of this turbulent inertia term. And we pick the decaying portion here because then there's a 1-to-1 correspondence between that and the y axis. Okay, so it's really a coordinate transformation. And we define this parameter beta, which is everything in the momentum equation except the viscous term, and it's dominated by the Reynolds stress gradient term. And what we can show is that for every point on this curve, you can think of it as the seat of a layer of finite width. And on that layer of finite width, if we use local scaling parameters, we can construct an invariant form of the equation. And that equation, as the name implies, is invariant from layer to layer. And it's that construction that leads to a similarity solution over this domain. And more particularly, I'll tell you, it's a subdomain of that. And this is a genuine similarity solution of the mean momentum equation. An important thing is that these layer widths are finite width, but they vary continuously. And we'll take advantage of this finite width. And that finite width means that the equations are leading order over that finite width. So that approximation holds over a finite width. And then you can do some scalings, okay? And this is, again, skipping a number of steps. But there's these scaling parameters that allow us to go from plus variables to the hat variables that are express the invariant form. And so we have alpha, gamma, and lambda. And if you go ahead and look at the balance on each of these layers, it behaves like that layer 3 where all 3 terms are of leading order. So the construction is one where you want to find a representation of the equation where all terms are order 1. And this is the invariant form that exists on each layer if you go through this process. The conditions that lead to that are this, and you can see that alpha and gamma are not completely determined because lambda is not been yet specified. And so at this point, we make an analytical decision, and I can talk about the empirical basis for this, especially for the canonical flows, that we set lambda equal 1. That is, physically means we're selecting u tau as the characteristic velocity, and that also ensures that the solution approaches a logarithmic one on the domain of interest. Okay, and so one can then go through a number of steps. You asked the question where the hierarchy layers reside. So this is that transformation that goes from y plus to y beta, or the beta, what beta value corresponds with each y plus. You begin with this expression, which is exact, differentiate with respect to beta, normalize on the local coordinates. So now we're using w effectively, and the seat of each layer. We're evaluating this gradient there. And an important thing is you go ahead and you define this second derivative. And the analysis shows that this normalized second derivative of the Reynolds stress is known to be, is order 1 for all beta. Okay, so meaning it's bounded by 2 constants as epsilon goes to 0. As the layer hierarchy grows, though, it's rational to expect that quantity to not just be bounded, but to actually become a constant. And I can talk more about that if you like. And so what we end up with is this bottom expression, and this leads to the sort of the fundamental condition for asymptotic self-similarity, is that if we assume A equal constant, so that's the key assumption, it's not just bounded but constant, then we can go ahead and integrate that expression. And what we can show is that the layer widths scale with distance from the wall on an interior domain of the hierarchy, and in terms of the asymptotic approach to that, you'd expect it to scale as that to get better and better as the Reynolds number goes to infinity, the linearity of that function. And this, within this theory anyway, is the origin of distance from the wall scaling. Okay, another thing you can do is, so we'll go ahead and plot W here in a second. You can define dw dy as something we call phi sub c. It's a scaling parameter, which will become clear in just a second. C just refers that it becomes constant. If you invert that, then you have basically the coordinate stretching. dw dy, we're normalizing y by w. W is physically the wall normal scale of the turbulent motions responsible for wallward momentum transport. And that's equal to phi sub c, and it's effectively the coordinate stretching that's telling you how those motions are stretching in space. Okay, so here's W, and we've plotted it here for Reynolds number going from about 550 to about 10,000. And if you look on the inertial domain here, especially we look mainly at the Yamamoto and Tsuji data at 8,000, you get linearity within about 4 parts in 10,000. So that speaks to the veracity of that key assumption. The other thing you can see here is that where these begin to show linearity, so we're normalizing by y here. The other thing I note here is I'm pointing out a capital phi minus 1. That's actually the golden ratio, and I'll tell you how that enters into this in a second. It turns out phi sub c is very close to the golden ratio. So now that we have that construction, we can go ahead and invoke the mean vorticity equation, and that allows us to either express our similarity condition in terms of u or t independently, and then we can independently integrate those to get independent solutions for u and t. A couple things to note here. In the u case, you see the leading coefficient is phi sub c squared, so it's directly related to the von Karman constant. And this quantity c sub c2 needs to go to 0 if you're going to recover the classical log law. It turns out it goes to 0 like 1 over the Reynolds number squared, about like that. The other thing to note is the T solution also contains phi sub c. So if, in terms of theory, you could determine the von Karman constant just as validly from the T solution as you can from the U solution. Okay, almost done with the sort of the background. Sorry, this is taking so long. The other thing to note, and this goes to the finite width of these layers, is you can actually do a discrete construction of these layers because they're of finite width, and you can just have them abut against each other without loss of generality. And this is actually the Yamamoto data. And the reason they all look about the same width is because we plotted it on a log scale. And so if it's about linear, that's what you're going to get. Okay, so we have this discrete hierarchy construction. And before I get into looking at the Reynolds stress fluctuations, I just want to show that this stretching coefficient is actually impressed in the solution structure of the Reynolds stress. So here's the Reynolds stress profile very near the peak. So we're looking at very fine details of this solution. In light gray is the solution from the DNS. In dashed line on top of that is the solution that I presented for T earlier using phi sub c equals phi, capital Phi, the golden ratio. So it's very close. One of the properties, and I could possibly talk about others, is that if you take the solution for the T from that I presented previously, you can show that if I pick a point on this side of the peak and a point on this side of the peak at the same value and take its geometric mean, it recovers the peak value. And so that's what this shows here, is we're picking points along the curve. We pick points along the curve here. And from the theory, you can also show that the peak value is in fact phi sub c square root delta plus. And the values that you see in the middle there are the computed values. So they don't fall exactly on the line, but they all fall within a fraction of a viscous unit from that. And so this sort of shows, and it predicts that phi sub c is equal to 1.6195 and a von Karman constant of 0.3813 if you use those. The other thing I can show really quickly is, well, no, I'll go on. I'll maybe talk about in a second. So this is this business about how it's related to the golden ratio. So for those people who know, if I take this blue line and red line, and they have the properties that A over B is equal to C over A, and A plus B is equal to C, then that ratio of those two, A over B, is the golden ratio. In the present layer structure, we have, in the discrete representation, we have yi, and then yi plus wi gives you yi plus 1. And so, but we only have 2 of the 3 conditions here that we can actually show. And so we just arrive at this. Now, if phi sub c squared over phi sub c plus 1, it goes to 1, as Reynolds number goes to infinity, then phi sub c does go to capital Phi. That's just simple math, okay? The physical implication of that is that the layers become self-replicating, and that is wi plus 1 is equal to yi. And it turns out for this Yamamoto and Tsuji simulation, it's very closely shown. So this is a position that's at square root Reynolds number. If I apply the use phi to compute to get to here, I get to that point, which is a small fraction of a viscous unit from that center point. And then if I do it again, I recover there, and this length is square root Reynolds number. Okay, so this is a self-replicating flow to a very high accuracy, the Yamamoto and Tsuji DNS. Okay, from these thoughts, we have a couple of conjectures, and I don't have time to go into these in detail. One is that the negative UV time fraction or area coverage in the DNS is equal to 1 over phi sub c in this inertial domain. And effectively, that's the time spent in Q2 and Q4. And it has to do with competing changes of scale while the momentum transport has to be equal. The second one is, and less well understood, is the conjecture that the negative UV skewness is equal to minus phi sub c. And this has to do with the size of an event and its magnitude of a negative UV fluctuation. And I won't have too much time to talk about that. In fact, that's all I'm going to talk about it, and to show you the data. Okay, before we can do that, we need to know where the inertial layer is. Inertial layer for these flows is order square root delta plus out to about 0.15 or 0.125 delta. And just because I think it's interesting, there are a number of properties that correlate with this. And I just show these here up to very high Reynolds number. These include the skewness of U, zero crossing, the spectral, pre-multiplied spectral peak, difficult thing to estimate, the U squared outer peak, the correlation, the modulation correlation coefficient, zero crossing, and the UV peak. And they all kind of scale in the same way at these intermediate variables. So this is the onset of the inertial layer, something about 1.5 square root delta plus. And that's what we use because we're going to do some averages over the inertial layer. Okay, so let's jump into the data. We're going to consider data from the high Reynolds number boundary layer wind tunnel at Melbourne, the flow physics facility at the University of New Hampshire, and the Klewicki pipe in Bologna. These are measurements by Morrow-Winter 17 and Zimmerman et al. 2019. And one employed a 4-wire probe and one employed an 8-wire probe. I'll talk a little bit about the data quality here in a couple minutes. So let's go ahead and just take a look at the negative UV time fraction. So on the left here, we have the data from Yamamoto and Tsuji. This is DNS between 1,000 and 8,000. We've normalized Y by square root delta plus. So if we pick a point starting here and go out to about to here, that's our inertial layer. You can see with increasing Reynolds number, the curves drop down and sort of flatten a little bit. If we take the average over the inertial layer, we get a curve that looks like this. So it's dropping down toward that 0.62 value, 0.618, but it's still changing as we go with increasing Reynolds number. You see a similar behavior from the pipe and boundary layer data. The boundary layer data of Morrow-Winter shows an almost identical trend as the Yamamoto and Tsuji. In other words, it's dropping down, whereas the Zimmerman data scatters a little bit. This has to do with the accuracy of the processing of the X-array and having an independent U measurement in getting that. And for those who are interested in experiments, I can talk more about that later, maybe. So this all looks pretty encouraging, but there's still variations. And so one could question, you know, at a high Reynolds number, is the value way down here or something like that? So we went to the atmospheric surface layer and we looked at measurements from measurements we took out on the salt flats and other studies that have reported on those, as well as the data from the QL08 facility in China by Wang and Zhang. They were kind enough to give us their data. And these are the results for T24, so the time fraction. And what you can see is that most of the data fall with about plus or minus 5%. They tend to be slightly low. That, we think, is primarily due to the fact that there's misalignment with the mean flow direction, and any misalignment is going to cause that value to drop a little bit. In fact, we had to sort of filter the hot wire data because we didn't have any way to align it with the mean except visually with a little tag. But then we were able to select a subset of the hot wire data that had agreement with the UV from a wind-aligned sonic within plus or minus 10%. And those are the colored symbols, whereas the black background gray symbols are the totality of the hot wire measurements. One data set that I'd like to especially impress upon you is the one reported by Hutchins and Marusik. I was on the salt flats then. I was there that day. That was a beautiful day. The wind came out of the north at a very steady speed and for a long period of time. And if you look at these data points, 7 of the 8 actually touched the line. So that was nice. I like that data set. I'm allowed to do that, right? 5 minutes? Okay. So if we go ahead and look at the skewness of U, I've got them all plotted on here at once, or skewness of UV. You see with the Yamamoto and Tsuji data a very similar trend in that they're kind of off from the asymptotically conjectured value and then get very close to it and sort of track it at the higher Reynolds numbers. Scatter around the value conjectured from the experimental data with a couple of outliers. That's clearly something wrong there. And then, as one might expect, the skewness of UV data from the atmospheric surface layer are more scattered. It's very difficult to do high order moments when you have limited time at near neutral conditions. But overall, the data seem to suggest no bias about that value, with the value of minus 1.6 kind of going through. Okay, so this all looks good. We don't fully understand it, but it seems to be in line with the conjectures. The last thing I wanted to talk about was trying to understand what is it about the properties of these UV fluctuations that lead to these behaviors. And so we did a Graham-Charlier analysis of the UV PDF. In recognition of this, T24 is just a negative integral of that PDF, whereas the skewness, of course, is this property of a PDF. And so they're both can be derived from the PDF. And so here we show delta plus 2400 from, I think this is the Melbourne wind tunnel. And then we have the DNS at 8000. This is from the FPF, so another boundary layer. And then we have the PDF as derived from a hot wire signal out on the salt flats. And what's noticed here is, so the dashed lines are the fourth order corrected PDF. So we're including non-Gaussian effects in the U and V statistics, and that's the dashed line, whereas the solid line is if we assume Gaussian statistics. And what's remarkable is the agreement with Gaussian statistics on the negative side, whereas on the positive side, you see significant deviations. And just in case we're wondering if how they agree with each other, that's plotted down here, and it's remarkable that these negative fluctuations are self-similar over an enormous Reynolds number range. So this is a pretty solid evidence of the universal property of the UV fluctuations. We can look at the Gaussian approximations. I guess the dirty little secret there is that neither U or V are Gaussian at these Reynolds number, even at the salt flats Reynolds number. So it doesn't like they approach, it's not like they approach Gaussian with increasing Reynolds number. They're not quite Gaussian, but regardless, let's go ahead and look at it. So this is the formula for this probability density function if you assume Gaussian functions. And so the two things there are the correlation coefficient and the 0th order modified Bessel function. If you compute the negative time fraction from this formula, then you just get this. And so, for example, at delta plus of 16,400, we get a R value of 0.3277. T24 as measured is 0.6161. And if we use this formula, we get a value about 2% away. On the other hand, skewness behaviors require the non-Gaussian correction. Again, however, I say that these that neither U or V are Gaussian. And so there's something else going on here. Lastly, because the correlation coefficient shows up in this, we wanted to look at the correlation coefficient. And so here we present correlation coefficient averaged over the inertial layer for the laboratory and DNS data. And we plotted it both against the log law and against small power law. And the small power law comes from the recent suggestion of Chen and Srinivasan. And you can actually show from a scaling analysis if the U fluctuations adhere to this minus power law scaling, so the peak in U, then you're going to get a behavior like this. And what it shows is that the data seem to suggest that this minus quarter power law, as suggested by Chen and Srinivasan, better fits the data. So with that, I'll go ahead and summarize. I guess the main things is that it seems like there's some evidence that the self-similarities reflected in the mean equation solution are actually embedded down in the turbulence properties, and that within the data scatter, the conjectures are consistent with the measurements up to delta plus order 10 to the 6th. The Graham-Charlier analysis shows that the negative UV fluctuations are invariant with Reynolds number, essentially, and the correlation coefficient seems to be consistent with the recent ideas of Chen and Srinivasan about a bounded dissipation. So I'll go ahead and stop there. Thank you.
Okay, time for questions. A little bit of a late start, but
I just wonder, actually, you show that the UV PDF actually fit quite well with the Gaussian approximation. But
yes.
Usually if you measure the PDF of the isotropic turbulence, you have a long tail. So that's a kind of sign of the intermittency in the flow. So, but I just wonder whether you calculated the UU PDF. And then can you?
So yeah, I mean, we've looked at the individual U and V PDFs, and they're non-Gaussian.
They're not Gaussian.
Right? So if we assume those are Gaussian and we construct the UV PDF, then we get what seems to be very good agreement on the negative side, even though those PDFs are not
Okay.
Gaussian. And so there's something going on there that we need to look more deeply into. There's, maybe it's just the Gaussian motions that are contributing to that. I don't know.
Or
Right,
the
but-
intermittent motion does not have Reynolds shear stress or something like that?
But
or-
something like that, right?
Okay.
There's, it gets down to the question of how do U and V get together to create Reynolds shear stress?
Okay, thank you, Joe. Well, I like the idea that you're combining, so to say, asymptotic ideas and with similarity. However, I would be more inclined to believe what you showed, even though I could not follow all the details. If you would look at higher moments, I mean, see the equation you started off with is still an unclosed equation, right? There's this enormous possibilities. So, however, if you go to higher moments, that will shrink your the possibilities significantly.
Yeah, we
Did you
haven't
ever see-
done the analysis to try to develop invariant forms of the higher order equations.
Because that would be very interesting. Then I think you really made a major step, I think.
Last question from Pavia.
Yes, I mean, when you say that the PDF of U and V are not Gaussian, do you mean that they are super Gaussian or sub Gaussian?
So U is sub-Gaussian
Sub Gaussian, yes.
and V is slightly super Gaussian.
Yeah, I mean, U has always been sub Gaussian.
Yeah,
I mean, it's
and
not
we-
an intermittency effect.
Originally, we thought, okay, maybe if we go to really high Reynolds numbers, that'll change. And
No,
we
it
get
doesn't.
exactly the same, 2.8 for the
I mean,
for the
those are the largest
kurtosis.
scale. Those are the largest scale. The largest scale.
Yeah, yeah.
Right, let's thank Joe again for a very good talk.
Leave that.